Hey guys, welcome back to the third part of the Chemical Equilibrium Series. In this video, we're going to be talking about the reaction quotient. So the reaction quotient Q is a value that tells us the concentration of products to reactants at a particular time. And I'm going to underline this right here because that's a very important part of the definition. Notice how this definition here is very much similar to the definition of an equilibrium constant, right? K, which is what we had talked about in the second video. So if you haven't seen that, please go check that out. But the difference between the reaction quotient Q and the equilibrium constant K is that K is at equilibrium, whereas Q is talking about at a particular time. So it could be at any time during the reaction. And if you notice here, the way that Q is defined mathematically is identical to the equilibrium expression K, right? You're going to write out your products on top over the reactants on the bottom. And of course, you're going to include your coefficients as the exponent of the molecules, okay? And again, I wrote here that A, B, C, and D are concentrations at any time during the reaction. So Q is very important because when compared with the K constant, Q can help us figure out which way a reaction will proceed. Okay, it's a very powerful tool. And so if Q is greater than K, the reaction is going to shift to the left. If Q is less than K, the reaction is going to shift to the right. If Q is equal to K, there's no shift because it's at equilibrium. And also, much like K, Q is unitless. And when you're writing out the reaction quotient expression, you do not include solids or liquids. So let's fit Q into our pizza analogy. So remember, Q is equal to, again, your products over your reactants, but at any time. So let's say at this time right here, initially you're given 5 slices of pepperoni and 3 sausages, right? And no pizza to start off with. And you're going to put it into the system. And after a certain amount of time, the system reaches equilibrium, in which you'll have a constant concentration of your pepperoni, sausage, and pizza, right? Remember, at equilibrium, you get the K constant, right? So you'll have some value. Let's say, oops, let me do this in turquoise. So let's say for the K constant, you have a value of, let's say, 3, okay? Going back to the reaction quotient. So let's say when you plug in your products and reactants initially at this time, let's say you have Q is equal to 1. So if Q is equal to 1 and K is equal to 3, right, that means Q is less than K, and the reaction is going to have to shift to the right to get to K, right? So basically, Q is always playing this game of catch up with K. Let's say we have a different case in which you were given, for your starting, let's say we have a different case in which for the starting ingredients, you get 5 slices of pepperonis, 3 sausages, and let's say you get like 12 slices of pizza, right? So clearly there's a lot of products, right? So that means your Q is going to be a lot bigger, right? Because it's products over reactants. And so let's say you have, let's say you have 5, right? So if you compare Q to K now, Q is greater than K. So that means the reaction here is going to have to shift left to make more reactants to reach equilibrium. So down here, I've made another illustration to help you guys visualize this relationship between K and Q, right? Left-hand side, I have the reactants, right-hand side, the products. Let's say in the first case, Q is greater than K, so it's further right on the number line, right? So in order for K to get to Q, Q is going to have to shift left. So you're going to make more reactants to get to K. And on the other hand, let's say Q is less than K, right? So then Q is going to have to shift right to make more products to get to K. All right, guys, we are going to tackle our first example of this video. So part A is to write a Q expression, right? So remember, the Q expression is very much like the K expression. All you're going to do is write down the products. So I have the concentration of N2. It's gas, so I can include that. It's raised to the first power, so I don't have to write that, times your next product, which is H2O. Again, that's going to be squared, right? And it's a gas, so you include that. divide that by your reactants. My first reactant is NO squared because of the coefficient. Then you have H2 squared because of the other coefficient. And so basically I'm including all 4 of these molecules because they're all gases. Remember, you do not include solids or liquids. Part B wants you to find Q given the initial concentrations. Notice the word initial, right? Remember, because Q is a measure of the concentrations at any given time during the reaction, whereas K is only during equilibrium. So you're going to plug these guys into the equilibrium expression that we had found in part A. And when you do that, you get this right here. Okay? So you plug in the values and you get 0.094. So part C is asking which direction will the reaction proceed. So in order to do that, all you're going to do is compare your 2 values of K and Q. So Q we had just found when we finished part B, which is 0.094. K we got in the second video of the series for the K constant, so which is 0.0039. So clearly Q is greater than K. And based off of our rules, if Q is greater than K, that means the reaction is going to have to shift left in order for it to reach equilibrium, right? It's going to shift left to make more reactants to get to equilibrium. And that's going to conclude the third part of this series. We finished up with reaction quotient today. And in the next video, we're going to talk about Le Chatelier's principle.